Welcome to our video, where we want to show you how to use SD cards in an embedded environment. In the previous video, we reviewed the physical layer of the SD card's SDIO communication protocol, and now we're going to dive in and try to read and write data with our microcontroller.
Our goal is to create a software that writes the natural numbers between 0 and 255 two times to the 512-byte long second block of the SD card, then reads it back, and compares the sent and received values. If the two data match, LED 1 lights up, otherwise it flashes. In the case of any other error, the software will flash LED 4 and will not perform any further operations.
Be especially careful not to write code that constantly rewrites the same block, as this can very quickly damage your SD card.
Now let's take a look at our hardware setup. The push button and LEDs shouldn't surprise you, as we've used them before. However, the SD card slot might be new, and we'll show you a schematic that shows how to connect it. There is also a light sensor, which we will use in our last example. By the way, this can be replaced by any other type of sensor.
Connecting the SD card slot doesn't really require any special talent. Just connect the pins to the corresponding pins of the microcontroller, as shown in this schematic.
Now let's see our software. First, import the attached project Lecture 23 block into the STM32Cube IDE development environment. Open the IOC file and see exactly what settings are in it. Among the microcontroller legs, we need the clock source, SWD, LEDs, and SDIO pins. The SD NDC signal is generated for us by the SD card slot. If there is no SD card in the socket, the SD NDC signal is low, and if there is, it is high. We will not need the HMI BTN3, which is push button number 3 in this example, but we will need it in the next ones. Because of this, we have already added it to our project for simplicity.
The GPIO signals are uniquely labeled for ease of understanding and are configured as output or input according to their function. On the PE3 leg, where we connected the button, we will enable the built-in pull-down resistor.
The SDIO interface is configured for 4-bit mode and 400 kHz CIK frequency. The clock frequency is generated by the SDIO peripheral from the 48 MHz system clock signal. The division rate can be set between 1 and 255. Based on the reference manual of the microcontroller, the CIK frequency is obtained by dividing 48 MHz by the division factor plus 2, meaning to reach 400 kHz, the CIK DIV should be 48 MHz divided by 400 kHz minus 2, which is 118, which we can set here in the STM32Cube IDE.
For the rest of the curriculum, the use of FreeRTOS will be essential. So just to get used to it, we will be using it now. In the attached project, TIM14 is used to generate the health timestamps. SysTick is used by FreeRTOS.
We will then regenerate the project to be on the safe side.
I should note here that in some versions of Cube IDE, the code generator makes a mistake and initializes the SDIO peripheral with 4-bit mode. This is a problem because according to the standard, communication with the SD card must be established in 1-bit mode, and only then can it be switched to 4-bit mode. The solution to this problem is to open the sdio.c file after generating the code and look for the value of the hsd.init.bus byte structure in the mx sdio sdinit function. This must be sdio bus wide 1b. If it is not, then rewrite it to this.
In order to facilitate the development, a framework software is already prepared in advance. Basically, we only need to work in the sdblocktest.c and sdblocktest.h files. The parts to be implemented are indicated by to-do comments. It's worth opening the files and reading through their contents, but the to-do comments can be listed by STM32Cube IDE if we click on the Tasks tab.
The SD block test task is already created in the main.c file, and is started as soon as FreeRTOS starts.
At this point, we suggest you to stop the video and implement your own ideas and solutions. And now I will ask my colleague to plug in the USB cable into the laptop. The software is already uploaded to the microcontroller, and as you can see, the first LED is already lit up. If it doesn't work out for you, then take your trusty debugging skills and use breakpoints to find out where your software is getting stuck. If you feel desperate, then you can find the complete software on our website under the name Lecture 23 Block Example. This is just an example of implementation. Beside this, there are a bunch of ways you can write the program.
Keep in mind that every time you run the program, you rewrite the second block, which means you reduce its lifetime.
If you're curious, you can use the debugger to look at the contents of the SDTX buffer and SDRX buffer blocks before and after the read. You should see something like this.
It seems that with a few simple function calls, we are able to read and write blocks on the SD card, and even the second block already contains the numbers 0 to 255 twice in a row.
In the next video, we'll take a closer look at what our computer can see from these data. Meet you there! Bye-bye!
Bye!